Good afternoon.
Afternoon.
All right, so you should have noticed that I posted your exam grades. Okay, so those are up online. I haven't had a chance, just because I finished so shortly before my first section of heat transfer. I need to scan in and post the exam solutions. Okay, so I know some of you have emailed me questions about it. I haven't even had a chance to open them and take a look yet on your questions on the exam of what you've emailed, commented on. Okay, so wait and take a look at those solutions. All right, and then the homework for Chapter 6, you should have noticed, was pushed out, I think, until Thursday. Okay, so you have a little bit of time on that. And then we have today, we'll be covering some examples from Chapter 6. Okay, so let's get started. Let's do, and we'll get to some of Chapter 7, but we'll start with 6.2. All right, so with 6.2, in flow over surface, velocity and temperature profiles are of the forms, and they give us an equation for the x direction velocity, so that's u, as a function of a polynomial, and then they give the temperature profile as a function of y with a polynomial, right? So, and they have where the coefficients a through g are constants, obtain expressions for the friction coefficient, CF, and the convection coefficient, H, in terms of free stream velocity, free stream temperature, and appropriate profile coefficients and fluid properties. Okay, so we're given flow over a surface, okay, and then they give us these equations. U as a function of y, a times y plus b y squared minus c y cubed. And then temperatures, function of y is equal to d plus ey plus f y squared minus g y cubed. And a through g are constants. They want us to find the friction coefficient, so that's CF, and the convection coefficient. And that's H, right? So basically we have let's redo that. We have a surface. And we have our velocity distribution. And we have our temperature distribution over here. Okay. And then there's also just our free stream velocity. And our free stream temperature. All right. All right, so we have this flow over the surface. They give us equations for the extraction velocity and the temperature, right, profile. They want the friction coefficient, the convection coefficient, and they want it in terms of U infinity, T infinity properties and the coefficients. So this, and the constants, let's say. Coefficients, constants. That's the A through G. Space this out a little better. So this is our analysis. And our analysis, where do we want to begin? Where are we going to start? All right, so as a beginner here, we're looking for the friction coefficient. So let's at least start there, right? Let's write what we got down here. Friction coefficient. Okay. So that would be CF, the shear stress, density, free stream velocity, which is squared, divided by 2, okay? So if we look at that, it said we can use properties. So density is fine, okay? Free stream velocity is good, okay? 2 is obviously good. We need shear stress, then, okay? Show shear stress at the surface. Looks like this, right? Again, this is dynamic viscosity, so that's a fluid property, so we're good there. And then we have this term. So what do we think we need to do?
Take the partial derivative of y, like from the equation that we've got for the fluid velocity.
Yep. So we have the x velocity, right, u. So we need to take the derivative, okay, and that gets us a plus 2by minus 3cy squared. And then at y equals 0, what do we get then?
Just A?
Yeah, we end up just with A, right? If we put that all together, we'll get a shear stress of A times the dynamic viscosity, and then a friction coefficient. And it looks like that when we substitute it all together. And we're good here, right? It has coefficients and fluid properties and the free stream velocity. Okay, we could also combine a property and do the kinematic viscosity instead. All right, that's just combining these two. Okay, so that's our answer there. And then we have now the convection coefficient. So our equation for that involves the temperature profile. Actually, let's do it the same way I did above. Looks like that, okay? So when we look at this one, we have the thermal conductivity of the fluid, so that's allowed. T infinity was allowed. Temperature of the surface isn't, okay? Or, again, the dt dy at y equals 0 is not allowed again. So we got to find that one out, okay? So with that one, we'll just do the same process. At least I'll show that one. Since it was the same, I'll just go through it quick. We got E 2 Fy minus 3 Gy squared. And at y equals 0, we just end up with E, right? All right, but we still need to get rid of the temperature of the surface. Any ideas on that?
Is that the temperature distribution at y is equal to 0?
Yep, yep. Yeah, so if we're just looking, then the temperature of the surface is just T at y equals 0, which ends up just being D, right? We would have an equation then for our convection coefficient. Okay, so if we were able to measure the velocity profile and the temperature profile, right, do some measurements of velocity and fit a polynomial through it, like we see here, it's easy right from the polynomial to get those friction coefficients and the convection coefficients. So once you have the polynomial, it's easy. Getting the polynomial itself is the difficult part in experiments. Any questions? All right, so let's do 6.8. What we got? 6.8. Laminar flow normally persists on a smooth, flat surface until a critical Reynolds number value is reached. However, the flow can be tripped to a turbulent state by adding roughness to the leading edge of the plate. For a particular situation, experimental results show that the local heat transfer coefficients for laminar and turbulent conditions are, and they give us an equation for the convection coefficient, the local convection coefficient for laminar, and they give an equation for turbulent. I'll write those in a minute. And they say calculate the average heat transfer coefficients for laminar and turbulent conditions for plates of length L equal to 0.1 meters and 1 meter. Okay, so we have laminar flow on a smooth flat, or sorry, we have a smooth flat surface. Let's just start with that. Okay, so we have our smooth flat surface, or it says flat plate, I should say, in this one. And they give us the local heat transfer coefficients. And we have laminars. And then we have turbulence. And then they want us to find the average heat transfer coefficient, and that's H bar for laminar and turbulent, in length of 0.1 meter and 1 meter. All right, so I'll draw our schematic over here. All right, so we just have a flat plate. We have our free stream temperature, free stream velocity coming in. And then boundary layer is created. Here's where X starts, and then our length of our flat plate. Okay. To steady state. All right. So we're have our flat plate, and the conditions are either laminar or turbulent, and we're given the local, right? And we need the average. So what do we do, or where do we start? Okay, so we're looking for, always, if you're unsure, start with what we're trying to find, right? So we have the average heat transfer coefficient. Okay. Well, there's an equation that relates to, and there's one for specifically for a flat plate. You're just taking the local, so this is for a flat plate, and integrating, okay, over that. Okay, so we have, right here is our local, and here's our average. All right, so if we have this now, we can kind of see where it takes us with what we're given, right? So if we first look at laminar, we can kind of think of the laminar equation as just a coefficient, the coefficient being a lam of 1.74, x to the negative 0.5, right? That makes it a little easier on our equation here. Okay, because now we just have this coefficient. We don't have to think about it as a number and worry about those numbers, okay, until the end. So we can integrate, resubstitute, and solve, and we'll get .48 watts per meter to the 1/5 Kelvin over length to the 0.5. Okay. So at L 0.1 meters, we get 11 watts per meter squared. 1 meter, we get 3.48 watts per meter squared Kelvin. Okay. So then it just becomes a similar process for the turbulent. This was coefficient with x to the negative 0.2. All right, so we get our new equation when we integrate, resubstitute. We get our convection coefficients. Okay. And we see, the shorter length has a higher convection coefficient, longer length, smaller average convection coefficient. And that's because the convection coefficients, start high and then drop, right? As we saw in our lecture. Any questions? Okay, I got one last one I want to do from chapter 6. We got 6.21. Consider laminar boundary layer flow over a flat plate. For identical flow conditions, determine the entries not shown in the table below using the fact that the velocity boundary layer thickness over the thermal boundary layer thickness is equal to the Prandtl number raised to the power n. The pressure is 1 atmosphere for each case. Hint, see appendices A4 through A6. And then they give us a table with missing information, some information there, some missing. Okay. All right, so we have a laminar boundary layer. Okay. The Prandtl number, the equation they gave us is this, okay? Pressure is 1 atmosphere. And they say C appendices A4 to A6. Oh, and then they also give us the table, okay? Well, I'll put that afterwards. Find missing table info. All right, so what we have in our schematic is our flat plate. And we can have basically we have our boundary layers, and the top one could be the velocity boundary layer or the thermal boundary layer. And the bottom one could be the velocity or the thermal boundary layer. Okay, so it's either one or the other for each of them, right? All right, so we have our table we got to do here. So we got fluid, the temperature, and then a ratio of the velocity boundary layer thickness over the thermal boundary layer thickness. Need 4 rows. All right, so they give us air. They have 300, and then they have 0.89. Okay. They give us water as a liquid. It's at 350. And then they give us engine oil. With our ratio of 15.4. Okay, I start all the ones that were given. Okay. Velocity, boundary layer thickness, thermal, boundary layer thickness. So if with air, we have 0.89. So what is that telling us about the boundary layer thicknesses? Which one would be the higher one? Which one would be the lower one in our schematic? Go ahead, sorry.
Thermal's higher.
Yeah. So the thermal would be higher, right? Okay. If it's 1, they'd be the same, right? If it's greater than 1, the thermal boundary layer thickness is going to be smaller than the velocity boundary layer thickness, okay? All right, so we have, again, steady state. And let's start filling in this table, right? So we have this equation that was given to us above. That's the ratio, and it's the Prandtl number raised to the n, right? So if we start filling in, we need section that has water there, right? And we're looking for this ratio. Where do we think we get the Prandtl number? It ends up just being, oh, go ahead.
I was gonna say, is that a nu over alpha from
Yeah.
the tables?
Yeah, and they'll actually, in the heat transfer, they'll have it just there, okay? You don't even have to get to those two properties. They've already listed in the appendices the Prandtl number itself. So appendices, okay? So in this case, it's water, so we're looking for appendix A-6, okay? But then we still need this N, right? Any ideas on how we can get that? All right. Is there any information maybe in the table that might help us? Okay, let's take a look at air. Air has this equation, right? 2. So for air, we have a temperature, 300, so we can go in appendix A-4, okay, get it. And we have this ratio, which is 0.89. And our Prandtl number ends up being 0.707 raised to the power n, okay? So we can use that to solve for n. And it ends up being 1/3, okay? So now that holds true for any of these other situations because it's a laminar boundary layer, okay? For it just being a laminar boundary layer, that equation holds, okay? All right, so then back to the water. We get 1.32.
So even though they're different fluids, why is it the same exponent value?
It's just because it's a laminar boundary layer, okay? So that's why we work within these non-dimensional parameters like Prandtl number and like we have with, say, Reynolds number with stuff in fluids, because it non-dimensionalizes it, takes away that influence of the property of itself, okay? It's created this ratio all based upon a non-dimensional parameter. Now, if we had turbulent versus laminar, then that might have a different factor n to it, right? But in the laminar, they're all the same for this laminar flat plate. Okay, it's all PR to the 1/3. So we have figured out air and water, and now we have engine oil. It's missing a temperature, right? Okay, so we're given the ratio up here, 15.4, and now we have that 1/3, so if we rearrange for Prandtl number, we end up just getting 3650. So now what do we do with that number?
Go to the appendices.
Yeah, so we just go look in our appendices, and this one ends up for engine oils A5. And then that'll end up getting us our temperature of 309 Kelvin. Oh, the last one should have one more information. I forgot to write this. This should have 45.3 here. Okay. But we don't know its fluid or its temperature, right? So again, we can solve for Prandtl number. And what was it, 45.3 cubed. And we end up getting 93,000 for the Prandtl number. But from that, we need to figure out a fluid and a temperature for 93,000 on the Prandtl number. What do we do? So they were nice enough in this problem to give us a number that's really high, like 93,000, right? So then we can start just going to our appendices and looking for 93,000. That ends up being very high, and the only one that could possibly be it ends up being glycerol, or sorry, glycerin. And then the temperature that goes with is 272 Kelvin. Any questions? So that Prandtl number tells us a lot about what's happening with that fluid, right? So again, we said if that ratio is 1, they're the same, right? So that would be a Prandtl number of 1. Okay. So then Prandtl number greater than 1 or less than 1 will change what then that looks like, right? And we saw only the air had the thermal boundary layer higher than the velocity boundary layer thickness, while the others, all the velocity